Susana, anyone here?
I don't know yet.
Now that we have what I call a good fundamental understanding of chemical equilibrium, we are in a position to learn how to solve what we might call a number of classic types of problems that students are usually expected to be able to solve in a first-year high school chemistry class. You will probably be very shocked by the statement that I'm now about to make. You already know absolutely positively everything you need to know to solve, in principle, any equilibrium problem in the entire world. Because, as we mentioned earlier, the only thing you really need to understand is what an equilibrium constant is, how you write it, and what its numerical value tells you. But don't get too relaxed. In actual practice, equilibrium problems are so diverse and range so widely in their level of difficulty that you could literally spend an entire semester learning how to solve equilibrium problems and still not cover every possible type. So while in principle we have all the background we need to solve any equilibrium problem, in practice things aren't that simple. You need a lot of practice. You need a lot of exposure. You need a lot of experience in order to become good at solving equilibrium problems. So most of the remaining lectures are going to have as their focus these types of problems. But remember, there really aren't different types of problems. There's really only one problem, and it involves only a few basic concepts. But there's probably no topic in a high school chemistry course better than equilibrium at pulling together all the things that we've learned to this point. The first type of equilibrium problem students are asked to solve, I personally think is also the simplest. And that's where you're given the equilibrium concentrations of all the reactants and products, and you're asked to calculate the value of K. Here's an example. Consider the reaction between carbon monoxide and hydrogen to form methanol, CH3OH. Given the equilibrium concentration you see on the screen, find the numerical value of K. I said that I consider this to probably be about the simplest type of equilibrium problem. I would even go so far as to say that it's hardly an equilibrium problem at all, and it's more like an algebra problem. I mean, it is an equilibrium problem only in the sense that you have to know how to write down the correct expression for K. But if you know how to write the correct expression for K, this really comes down to just plugging the numbers in correctly and then using your calculator correctly. According to our rules, K would equal the concentration of CH3OH divided by the product of the concentration of CO times the concentration of hydrogen squared. So plugging in the numbers, the concentration of CH3OH was 5.05 molar, the concentration of carbon monoxide was 0.65 molar, and the concentration of hydrogen was 0.86 molar, and that has to be squared. This comes out to be a value on the bottom line, 10.5 if you want to carry an extra digit. Either answer is okay with me. And I'd like to make one comment about this problem and equilibrium problems in general. When solving equilibrium problems, we typically do not attach units of concentration to any of the substances in the equilibrium constant expression, nor do we include any units on the value for K itself, for reasons that are beyond the scope of this course. This is kind of in conflict with our normal practice of including units on all numbers. But if you try to include units in equilibrium constants, they will be of no use whatsoever, and will only serve to mess up everything. So units are not carried through the solution to the problem, but the proper units should always be attached to the final answer. Okay, let's try another. Given the reaction between sulfur dioxide and oxygen to form sulfur trioxide and the equilibrium concentration shown, find the value of K for this reaction. This problem is basically just like the last problem. The only challenge is to make sure that you write down the equilibrium constant expression correctly, remembering to square the concentrations of both sulfur dioxide and sulfur trioxide. Make sure you line up each of the concentrations given with the correct substance, and then make sure that you evaluate the expression correctly, which means remembering to raise each concentration to the appropriate power and using your calculator correctly. Plugging in the numbers given in the problem, the concentration of sulfur trioxide was 0.3 molar, and that has to be squared. The concentration of sulfur dioxide was 0.044 molar, and that also has to be squared. And the concentration of oxygen was 0.16 molar. If you evaluate this correctly, you'll get an answer of about 290, or 2.9 times 10 to the second in scientific notation. Okay, that's the first, and as I said, I think the easiest kind of equilibrium problem. So let's take a look at another type of problem, slightly different, but really very similar to the first two we've looked at. Let's go back to the equation we used for our first problem, the reaction of carbon monoxide and hydrogen to form methanol, for which K is equal to 10.5. Given the equilibrium concentrations of carbon monoxide and methanol that you see on the screen, find the equilibrium concentration of hydrogen. When I say this problem is related to the first two problems we've seen, what I mean is that in the first two problems, we were given the equilibrium concentrations of all the substances involved in equilibrium, and then we're asked to calculate K. This problem is just a little bit of a variation on what is basically the same thing. Now, instead of being given all the equilibrium concentrations and asked to find K, we are given K and Q of the three equilibrium concentrations, and then asked to find the third. So once again, this really is more of an algebra problem than a real chemistry problem. We said that K would equal 10.5. The equilibrium concentration of methanol was given as 2.33 molar. The equilibrium concentration of carbon monoxide was 1.25 molar, and we were supposed to find the equilibrium concentration of hydrogen, and that concentration is squared in our equilibrium expression. So there's the correct setting. All that's left is the algebra and calculator. We can solve this quickly or more slowly, depending on how good our algebra is. I'll do this first one rather methodically. First, we'll cross-multiply. So cross-multiplying, we get that 2.33 equals 10.5 times the denominator of equilibrium constant expression, or 10.5 times 1.25 times the concentration of hydrogen squared. Then, dividing both sides by 10.5 and 1.25, or rearranging the expression however you think of it, we get the concentration of hydrogen squared, and that's very important, is equal to 2.33 divided by 10.5 and divided by 1.25. Which equals 0.178. 0.178 is not the answer to the problem. That number does not equal the concentration of hydrogen. It equals the concentration of hydrogen squared. But our task was to find the concentration of hydrogen, and that would be equal to the square root of 0.178. So you need to know how to take the square root of a number on your calculator. Again, if you don't know how to do that, you'll have to consult a manual that came with your calculator, ask your math teacher, or something. Since all calculators are different, there's no way for me to provide specific instructions on how to do this. The square root of 0.178 comes out to be equal to about 0.42. And an important thing to remember is that after you obtain your numerical answer, be sure to put the proper units on the answer. The concentration of hydrogen isn't 0.42. It's 0.42 molar. And here's another slight variation. Solid silver chromate, Ag2CrO4, is in equilibrium with its aqueous ions, silver ion and chromium ion. The equilibrium constant for this reaction is equal to 2.4 times 10 to the minus 12, a very small value. Given the equilibrium concentration of chromate ions shown on the screen, what is the equilibrium concentration of silver ion? I'd like to make a comment here. You may have noticed that in the original statement of the problem, an AQ was put in parentheses after the symbols for the silver ion and the chromate ion. As we mentioned several lectures ago, this indicates that these ions were in solution in water. But I've eliminated this designation in the presentation of the solution to the problem, because it is generally understood that when nothing is written after the symbol for an ion, we assume that it's dissolved in water. This is done just for convenience, so we don't have to keep writing AQ time after time after time. Okay, let's see how this problem works out. The equilibrium constant expression for this reaction would be equal to the concentration of silver ion squared times the concentration of chromate ion. Note that there is no denominator in this expression, or more correctly, the denominator is understood to be 1. If you remember, in lecture 23, we learned that you never include pure solids or pure liquids in an equilibrium constant expression. Since the reactant here is solid silver chromate, it should not appear in the equilibrium constant expression for this reaction. So K just equals the concentration of silver ion squared times the concentration of chromate ion, and this is equal to 2.4 times 10 to the minus 12. The concentration of chromate ion was given in the problem and was equal to 3.8 times 10 to the minus 4th mole. We were supposed to find the concentration of silver ion. So all we really have now is an algebra and calculator problem. The concentration of silver ion squared, it's easy to forget that, is equal to 2.4 times 10 to the minus 12. Divided by 3.8 times 10 to the minus 4, which comes out to be 6.32 times 10 to the minus 9. So the silver ion concentration would equal the square root of that, or 7.9 times 10 to the minus 5th mole. And remember to attach the proper units to your final answer. So that brings us to another problem. At this point, you may be grinning like the proverbial Cheshire cat, thinking that these equilibrium problems are the easiest thing we've done yet. So let me warn you that the next problem is very, very different. So think carefully as you attempt to solve it. Consider the equilibrium system you see on the screen. 1 mole of H2S was placed in a 1-liter container and allowed to establish equilibrium. At equilibrium, the concentration of S2 was measured and was found to be equal to 0.15 mole. That's what's meant by the phrase, at equilibrium, square brackets S2 equals 0.15 mole. Calculate the value of K. And you notice that it says hints to follow if needed. Why does it say that? It says that because we are taking a quantum leap in going from the previous problem to this problem. If you are brimming with confidence, you might want to tackle this problem. But if you feel you could use a little help, instead of pausing the video at this point, watch these hints. The problem says that 1 mole of H2S was placed in a 1-liter container and allowed to establish equilibrium. What this is telling us is that I took a container, 1 liter in volume, and into this container I placed 1 mole of H2S. Well, I suppose it's fairly obvious that this makes the concentration of H2S 1 mole. So you may be thinking, okay, I get it. I just plug in 1.0 molar into the equilibrium expression for K. No, absolutely not. Au contraire, as I like to say, here's the most critical point. This is not an equilibrium concentration. This is what I put into the container initially. Now, you may recall that we said initial concentrations are indicated by putting a little subscript of 0 below the symbol for the concentration sample. I began with 1 mole per liter of H2S in the container. But when I want to calculate a value for K, I have to use equilibrium concentrations, not initial concentrations. K must be calculated from the concentration of all reactants and products after you get to equilibrium. So what does this mean? It means that the equilibrium concentration of H2S is not going to be equal to 1 mole. Because if I begin by only putting H2S in the container, some of the H2S is going to have to decompose and turn into hydrogen and sulfur in order to establish equilibrium.
Oh, here,
Because it's a very important point. If I put nothing but H2S in the container initially, and that's what the problem says, 1 mole of H2S is placed in a 1 liter container. That system cannot possibly be at equilibrium because there are no products. So the system is going to shift to the right. H2S is going to decompose to form hydrogen and sulfur. Now the problem tells me that when I finally get to equilibrium, the concentration of sulfur is measured and it is found to be 0.15 mole. And they want you to calculate the value of K. Now, if you go back to the original 2 problems that we worked.
Okay, that's a problem.